Okay. So we'll start here. Look at this system. There is one mass and two springs attached. Okay.
Okay, sir.
These two springs are actually in parallel to each other. Why? Because if you move this mass M to any side, say you move this mass M to left side, say by X, this spring gets compressed by X and this spring gets extended by X. Okay.
Yes, sir.
That means both will pull in the same direction. That means they are in parallel, right? Even if they are in parallel, if they are on same side, both will push by same force. Here both, one is pulling and one is pushing by same force. But because both are in same direction, that forces just add up. Basically, overall
Yes,
K will
sir.
become K1 plus K2. So that's why time period is 2 pi under root M by
M by K1 plus K2.
K1 plus K2. So effective K is K1 plus K2. Okay.
Yes, sir.
So I'm not doing everything. You should directly able to write this. Okay.
Okay, sir.
Even if you do by force method or energy, law of conservation of energy, method of law of conservation of energy, you will get the same answer. Okay. Clear?
Yes, sir.
What about these two? These two springs, are they in parallel or series? They are in parallel, right?
Yes, sir. Parallel.
So if you move this mass by X to the left side, both will get compressed by X. So both
Yes,
will
sir.
push by same force in this direction. That's why again effective K is K1 plus K2 here also. So in
Yes,
fact,
sir.
these two systems will behave similarly. Okay.
Sir, the first case were also parallel, no, sir?
First case was also parallel only.
Yes, sir.
It is appearing in series, but actually it is in parallel because mass is in between.
Yes, sir.
Now this case, these two are in series.
Yes,
You know
sir.
why?
Yes, sir.
If mass is compressed by X, okay, these two will
Yes,
not
sir.
get compressed by X. This will get compressed by X1 and this will get compressed by X2. And
So,
in
sir,
fact,
K will be equal to 1 by K1 plus 1 by K2, no, sir?
yeah, 1 by K will be equal to 1 by K1 plus 1 by K2.
Yes, sir.
As we saw in work power energy, we saw. If you want, you can just go back and check that. Okay. Basically, this
Yes,
will
sir.
get compressed by X1. This will get compressed by X2. And in fact, X1 plus X2 is equal to X. Okay.
Yes, sir.
So X1 will be equal to X into K2 by K1 plus K2.
Got
And
it, sir.
X2 will be equal to K1 by the compression of spring will be inversely proportional to their constants. With high, now, the spring with higher K value will get compressed by a lower amount, and the spring with lower K value will get compressed by a higher amount, right? That's why for X1 you will get K2, for X2 you will get K1. Okay.
Yes, sir.
So F1 will be how much? It is K1 into X1, right?
K1 into X1, yes, sir.
So it will be X into K1 K2 by K1 plus K2. Okay.
Yes, sir.
And if you look at the other spring also, you'll get the same thing. X into K1 K2 by K1 plus K2. And in fact, that same tension will remain in this thing. The same force will remain. That means throughout the line, you'll get the same force. That same force
Yes,
will
sir.
act on this mass, which is how much? K1 K2 by K1 plus K2
K1
into
plus K2.
X, which is
Yes,
equal
sir.
to MA, and minus sign also will come because it is a restoring force. So here you can just see that omega is what. Okay. So basically K is overall K1 K2 by K1 plus K2. Agreed? When springs are in series.
Yes, sir.
So in place of K, I'm writing K1 K2 by K1 plus K2, and
Got
it
it,
will
sir.
come out to this. What about this? These two are in series. This is in parallel. So first find effective K for series, which is what? K1 K2 by K1 plus K2, and K3 is parallel. In parallel, you just add it up, right? So it will be plus K3. Are you understanding? See, in parallel, we just added up na K1 and K2. Right?
Yes, sir.
Yes, sir.
So first consider this as one spring. So it will be K1, K2 by K1 plus K2 effectively. That those two springs together in series. And this is K3. Now this and this are in series, so you have to just add this. So you get effective K as this. Okay. Fine.
Yes, sir.
Okay. What about this? First these two are in parallel, then this is in series. So first you add these two. So it will be K1 plus K2 because they are in parallel.
Parallel.
This whole thing is in series.
Now 1 by
with this.
K1 plus K2 plus 1 by K3.
No. It will be K1 plus K2 into K3 by K1 plus K2 plus K3. Clear?
Yes, sir. I was saying the previous step.
Yeah. So it is.
Yes, sir.
These two are for this. This is the third thing. Okay. So these two are for this. So it is like, KA, KB by KA plus KB. Where KB is K1 plus K2. Understanding? And KB is K3. Clear? Okay. Shall we proceed?
Yes.
Okay. So little bit system which is little bit complicated because three springs are attached in three different directions. In fact, they are making 120 degrees with each other. So there is some symmetry, some kind of symmetry here. Okay, like sp2 orbital, you are getting. Okay. Now, if this disturbs from its mean position, some restoring force will act. Who will give that restoring force? All these three springs together will give that restoring force. Do you agree?
Yes.
So we will just move it in some direction and see what will happen. I'll try to move it down and see. Okay. So I'll move down, move this mass down by a small amount dy. Why dy? Because it is in y direction. Okay.
Yes,
So
sir.
what will happen? This spring will extend in this direction and these springs will get compressed. Are you understanding why they get compressed? Because you are bringing that down. So the springs, these oblique springs will get compressed and this spring will get elongated when you move object from here to here, mass. Clear?
Yes, sir.
Yes.
Now this spring will exert a restoring force here and these two springs will push because they are getting
Yes,
compressed.
sir.
Now, because this is complicated problem, what I do is I'll take a right angle triangle here. Okay. So this side is X, this side is Y and this side is R. And assume that these two lines are almost same because that dy is small. Clear?
Yes.
Yes, sir.
Now, I'll write the equation, Pythagoras theorem, x square plus y
Pythagoras theorem.
plus r square. Understand it? Now observe one thing, when the mass is coming down, r will change, y will change, but x will remain same. This x will remain same as this mass
sir.
comes down, because no matter where you come, that x will be same, right? Y will decrease and r will decrease, right? Y will decrease, r will also become little smaller, whereas x will remain same as this mass is coming down. Do you agree? Okay.
Yes, sir.
So x is a constant I have written here. Now taking derivative on both sides, what will I get? Derivative of x square is 0.
X is
Why?
a 0, sir. Yes,
Because
sir.
it is a constant.
Yes, sir.
Y square is 2y dy by chain rule.
Yes,
R
sir.
is 2r dr. This 2 gets cancelled. So what will remain? Y by r into dy is equal to dr. Do you agree? Okay.
Yes.
Now I want to write dr in terms of dy because the mass is moving by dy. Clear? Okay. So what
Yes.
is y by r? Look at that. Y by r. This is y and this is r. And understand that this is 30 degrees. You know why this is 30 degrees? This was 120 degrees. So this is 60. This is 60. This is 90. If this is 60 and 90 in the triangle, this is 30. Do you agree?
Yes.
So y by r is sine 30. Can you see that? Opposite side by hypotenuse. Okay. Y by r is sine 30. Right? Okay. Because it is opposite side by hypotenuse. This is 30 degrees. Clear?
Yes, sir.
So what will be dr? Dr will be equal to dy into 1 by 2 because sin 30 is 1 by 2, right?
Yes, sir.
Now the vertical spring extends by dy and the other two springs, they don't extend actually. The other two springs, tell me. Do you understand why they get compressed?
Sir, can you repeat the question?
Which question?
अभी जो बोले थे आप
कौन सा?
कुछ पूछे थे ना सर अभी आप?
नहीं, यहाँ पे the vertical spring extends by dy. The other two springs get extended बोल के लिखा मगर वो wrong था, compressed है actually, right?
Yes sir.
वही
Yes.
पूछा by dr, right?
समझ गया सर.
Now the spring, the vertical spring will exert force in this direction, which is equal to how much? Minus k dy. Do you agree?
Yes sir.
Minus k dy is because, you know, okay, I will not write minus because arrow is already drawn. Okay, so k dy force is exerted. Clear? So you are getting my point. So I will not write bar also. I am writing only magnitudes because arrow is already drawn. Okay. F2 will be kdr, F3 will be kdr because their compressions are dr and dr, right?
Yes.
And the directions of forces are like this. And what is the angle between these two? बोलो, ये दो forces के बीच में angle क्या है? 120.
120.
Yes sir.
Okay, fine.
120.
Now we have to add all these three vectors to find the net restoring force, right?
Yes.
And the displacement of mass is dy. Net restoring force will be in the upward direction. You can see that because those
Yes.
two oblique forces will also result in a vertical vector, right?
Yes.
Okay. So F net is equal to minus I am writing because they are in the opposite direction of y. K dy in the upward direction and 2 kdr cos theta. When two vectors have angle theta between them and if their magnitudes are equal, what will be the resultant? 2a cos theta by 2, right?
Yes.
So this is 2a cos theta by 2. So it will be 120 by 2. 120 by 2. Understanding?
Yes.
So it is 120 by 2. So tell me what is cos 120 by 2? It is cos 60, right?
Cos 60.
Cos 60 is how much?
1 by 2.
1 by 2. So basically what we have is, we have this 1 by 2 and 1 by 2 cancelled. So what will remain? It will be k dy plus k dr because this will cancel, right?
Yes.
But what is dr equal to? Half k dy. It is dr is equal to dy by 2, right?
Yes.
dr is equal to dy by 2. That we already found out here. dr is equal to dy
Yes.
by 2. So I substituted that. Okay. So if you add these two, you will get 3 by 2 k dy. 3 by 2 k dy. Because 1 plus half is. So if you write second law, ma is equal to minus 3 by 2 k dy. So a is equal to how much? Minus 3 by 2 k by m dy. So this is the standard a is equal to what? Minus omega square x equation of SHM. So basically in place of omega, what you will get? Under root 3k by 2m, right? So time period is 2 pi by omega. That's why it is 2m by 3k. Clear?
Yes.
Clear?
Yes.
Okay. Now I'll ask you one more question. You tell me what is the answer. I'll give you two masses. So one mass. I'll give you two masses. No. Okay. This is one mass.
Yes sir.
And I'll give you one more mass. Very good. I'll give you one more mass. So The other mass is something like this. Okay. Change the color. Okay. So these are two masses. Now there is a spring attached between them like this. So there is a support here, and between them there is a spring. Between them there is a spring like this. Okay. Now the spring
Yes, sir.
constant is K. Spring constant is K. This has mass M1 and this has mass M2. Clear?
Yes, sir.
So I'm asking what will be the time period of this system? What will be the time period of this system?
Time period of the system.
So actually, if you do the problem completely, you'll get time period as this. Time period is equal to, you will get some understanding when I write the answer. Under root M1, M2 by
M1
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 plus
plus M2 into K.
M2 into K.
Okay.
So this problem we already did. It was two masses attached with a spring in between, right?
Yes, sir.
Yes.
This is also actually the same situation, but the design is different. That's all. If you want, you can do it. Write the equation for energies and check. You'll get the same thing, right? Why? Because kinetic energy is half. How much? M1 x1 square, M2 x2 square, x1 plus x2 is the extension of spring. You are
Yes, sir.
understanding? Same story that we saw before, like this problem. Which problem? I think this one, right? So that situation is also different. Only thing is design is changed. Instead of giving masses, side by side, here masses are, on
One
top of
above
each
the
other.
other.
Clear?
Yes,
Okay.
sir.
Now, let me introduce you to a new kind of SHM, which is, due to torsional spring. What do you mean by torsional spring? This spring we don't extend, but this spring we rotate. You are understanding my point?
So like a pendulum.
No. So generally, what do? We extend or compress springs, right?
Yes, sir.
But this spring we twist.
Got it, sir.
We twist this spring. So basically, there is something attached at the bottom like this. Say a disc is attached. Okay. Now
Okay, sir.
this disc will rotate like this. Like this, it will rotate. You are understanding?
Yes, sir. Got it.
So this K is different K. This is not called spring constant. This is called torsional constant. This is called
Okay.
torsional
Torsional
constant.
constant.
So this is called torsional constant. So it will behave same like spring constant only, but when we extend a spring, it will give you a restoring force. But when you twist this spring, you give angular displacement to this spring, it will give restoring torque. It will give you restoring torque. Okay.
Yes, sir.
So the equation will be this. Equation will be tau. Tell me, what will be the equation? Instead of F equal to minus kx, now the equation will be tau is equal to, tell me, minus
I alpha.
k. No, that you forget later.
Okay,
Instead
got
of
it, sir.
k minus k
K
theta.
theta. Yes, sir.
Okay. So the thing is, this is for normal spring. When you extend or
Rotational
compress a
parameters.
spring, this is when you twist a spring. Okay.
Okay.
And the thing is, this K and that K need not be same. They can be different. Okay.
Yes, sir.
So instead of K for the first equation, I am writing K dash. Okay.
Okay, sir.
So actually, this is called spring constant. And this is called, tell me,
Torsional constant.
Torsional constant. Clear?
Yes.
And what about this? This is restoring torque.
Moment of force.
No, restoring.
Okay.
Like restoring force, we have restoring
Torque.
torque. This is restoring force, right?
Yes, sir.
So which we know already. I'm not mentioning it. Okay. Now tell me,
Yes, sir.
if moment of inertia of this thing is I, and be careful here. I you take about this axis. In physical pendulum, you
Yes,
take
sir.
about
Perpendicular.
no. In physical pendulum, you take about this axis when it
Yes,
is
sir.
rotated. But here you take about this axis.
Got it,
The
sir.
axis about which you are twisting the spring. Okay.
Yes, sir.
Clear? So tell me, what will be the equation? Tell me.
Minus k theta equal to
Tau equals to minus k theta.
I alpha.
Yeah, tau can be written as I alpha according to Newton's second law. Correct?
Yes, sir.
So I alpha equals to
Equal
minus k
to
theta.
minus k theta.
Now you can rearrange this and you can write alpha equals to
Minus k by I theta
minus k by I
into theta.
theta. Right?
Yes,
Now
sir.
this is instead of omega square, right?
Yes, sir.
Yes. So this is your omega square according to the standard form of equation, right?
Yes, sir.
This is your omega square. Now tell me, what is time period? Tell me time
2
period.
pi under root
Hmm.
I by K.
I by K. Clear?
Yes, sir.
Yes, sir.
So this is called torsional pendulum. This is called
Torsional pendulum.
torsional pendulum. Okay, fine. Now I will be different for different situations. If he gives you disc, you can write mr square by 2. If he gives you rod attached at the center, you can write ml square by 2l and so on and so forth. Understanding?
Yes, sir.
So I'll mention some examples. Okay. So this is M and R. M comma R, and
R.
it's a disk. It's a
This.
disk. So tell me.
T equal to 2 pi under root mr square by 2k.
P equals to
2 pi under root mr square by 2k.
mr square by 2k. Very good. Can you attach a ring like this?
No, we can attach through its periphery, but
What do you have to do if you want to attach a spring? Sorry, ring.
hang it vertically.
You cannot hang it vertically.
Okay.
But you can attach a ring by some thread. Okay.
Yes, sir.
So basically this ring, I'll make it little small. You can attach this using some thread or something. Okay. You are getting my point?
Yes, sir. Got it.
So something like this you can attach. Okay.
Yes, sir.
Something like this you can attach, light, which is anyway massless thread, so it will not affect the moment of inertia. Okay.
Yes, sir.
Okay, fine. Tell me, what is the time period? Tell
T
me.
equal to 2 pi under root
Mhm.
mr square by k.
mr square by k. Okay, fine. Next.
Now hollow sphere.
No. Okay, we'll do hollow sphere also. No.
Sir, inertia, moment of inertia of cone is 3 by 10 mr square, no sir?
Solid cone or hollow cone?
Solid.
Solid cone is 3 by 10. Yes. Hollow cone
Okay,
is
sir.
how much? Hollow cone.
Hollow cone is 3 by 8.
No,
3
it is
by 5.
mr square by 2 only. I told you,
Mr
right?
square by 2.
Hollow
Okay, it
cone
is
is just like
just
this. It
yes
is
sir,
just like
layer of
this.
disc.
It is, disc cut and displaced. Okay.
Yes sir, got it.
You cut disc into small rings and you pull the rings,
Yes
in
sir,
this
got it.
fashion. So for
Or if we compress
hollow,
a cone, we will get a disc.
yeah, if you compress the cone, you'll get a disc basically. Okay.
Yes sir.
So what about this? This is also a disc.
Disc sir here also.
Hmm. One thing I'll do, I'll write this on this side. I'll put this on this side. But this is different from the first problem. Remember?
Yeah.
The only difference is the moment of inertia is through a different axis here.
Yes sir. Perpendicular to that axis.
Hmm. Hmm.
Saying 7.
Tell me.
Sir, mr square by 4k.
Very good. Mr square by 4k. Why? Because you know what the moment of inertia of a disk is about its diameter. This is diameter. Can you see?
Yes sir.
So you can apply perpendicular axis theorem and do this. Okay, it is rotating something like this. Okay, it is rotating
sir.
about this axis. So I'll mention that axis, this axis, right?
Yes sir.
So that axis is basically diameter. So about diameter, the moment of inertia will be mr square by 4.
Yes sir.
So time period is 2 pi under root
mr
Under
square by
root mr
4k.
square by 4k.
mr square by
It can be
4k.
further simplified here this time.
Why? Okay, no need.
4 can be taken out
No,
common.
don't do
and
that.
all.
We'll always write
Okay.
in standard form because
Standard form. Okay sir, got it.
okay, 2 pi is always coming. We don't want to disturb that.
Disturb that.
Clear? What about this?
Yes sir.
Now this time I will give you a rod
Okay sir.
attached at center. So this is rod attached at center.
2 pi under root ml square by 12k.
Yes. So basically you just write the, okay, this is the axis of rotation, right?
Yes sir.
So I'll change the color. So this is the axis of rotation. So moment of inertia of any rod about this axis of rotation is ml square by 12, right?
Yes sir.
So time period is 2 pi under root m l square by 12. Okay. Clear?
Yes sir.
Okay, now I am giving you some systems. You quickly tell me what the moments of inertia are.
Okay sir.
Now the same kind of problems you can write for here. I'll write disk for solid sphere and hollow sphere also, right? It is easy, right?
Yes sir, easy.
Easy only. Just
2
substitute
by
the
3 and 2 by 5.
Okay. Now I am giving you some systems. You tell me moments of inertia. Sorry, time periods. Now here one spring is attached. First I'll give you some simple, and it is attached to a wheel. So I'll give you the wheel here, and this wheel is a solid cylinder. Suppose this wheel is a
Solid cylinder.
Solid cylinder of radius r, of radius r and of radius r and mass m. Clear?
M.
So I'm writing that m comma r. It is in pure rolling.
Yes, sir. Pure rolling.
Now,
Here we
whenever
equal to R omega.
no. Whenever you have pure rolling, then axis of rotation is moving.
Yes, sir.
So whenever axis of rotation is moving, you will have two components. One is what? Translational
Translational and
kinetic energy,
rotational.
rotational. So I don't want you to write all that, all the equations now. I want you to write
Okay.
the answer directly. So what you do is you write time period t is equal to, you write 2 pi.
2 pi
Okay.
under root.
The trick is simple. You write under root here because it is typical problem which we did already. Instead
Okay.
of m, okay, for just spring mass system, you'll write m by k, right? 2 pi
Yes,
under root
sir.
by k. But here, instead of m, you'll get two terms: m plus
M plus small m.
I by r square.
Okay. Yes, sir. Got it.
M plus I by r square. You know why? Because when you write two terms, you substitute the condition for pure rolling. Omega is equal to v by r. Okay, so that I by
Yes,
r
sir.
square will come out as common. You look at that problem once, which you did already.
Okay, sir.
I by
R square.
r square. Clear?
Yes, sir.
So you substitute here, you'll get clear this.
Okay, sir.
Now you know what I is for this solid cylinder about the axis of rotation. Oh, where
Sir,
is the
3m by
axis of,
2k under root.
no. What is the axis of rotation for pure rolling? This
mr square by 2.
mr square by 2. Correct?
Yes, sir.
So
Yes,
what
sir.
will be the time period? Tell me.
No, sir, I was saying the whole answer previously.
Okay.
T
Whole
equal to
answer
2
is
pi
how much?
under root 3m by 2k.
2 pi under root
3m by 2k.
3m by 2k.
Yes, sir.
Okay, fine. Now instead of solid sphere, solid cylinder, instead of solid cylinder, if I give you solid sphere, what you will do? Same
Solid
problem.
sphere. Just
Solid
inertia
sphere.
changes.
Basically, solid sphere, moment of inertia changes. So,
Yes, sir.
solid sphere. Tell me. What will
7m
be
by
I?
5k.
7m by
5k.
okay. We'll just mention what I is here.
Yes, sir.
Last problem also. Tell me what is I here?
mr square by 2.
Here what is I?
So 2 by 5 mr square.
Clear?
Yes, sir.
Agreed. Now I'll give you a little bit problem which is a little bit complicated. So try to
Okay.
do. So I'll give you disk. This is a disk. So moment of inertia for disk about the principal axis is same as moment of inertia for solid cylinder. Okay. So here one
Yes, sir.
spring is attached and one spring is attached at the top. Okay.
Yes, sir.
So one spring is attached here Another spring is attached to the center, like this.
Yes, sir.
I think this is the center, right?
Yes, sir. So this is a disk.
This is a disk.
Okay.
So there are two attachments to this disk. One is at the center here. Can you see?
Yes, sir.
So get a different color. Okay. Another is at the top.
Yes, sir.
Here. Clear? Now
Yes, sir.
they are free to rotate about these attachments. You are understanding my point?
Yes, sir. Got it.
So they are hinged here, basically, not hinged, I can say. They are attached such that there is a connection, but there is no restriction on rotation. Clear?
Got it, sir.
And here there is a rigid support. And at the bottom also there is horizontal rigid surface, but there is
Okay.
enough friction to ensure pure rolling. There is enough friction to ensure pure rolling. So here also pure rolling, here also pure rolling.
Okay.
Now I'll write K values differently. So the K for the top spring is what should I take?
What, sir?
K, I have to take two different values for K.
K1,
Okay.
K2 will take directly.
No. Okay, I'll take K1, K2. Okay, no problem. Okay.
Okay, sir.
So this has mass M and radius R. What was this? Disk, right?
Yes, sir.
So this was a disk of mass M and radius R, pure rolling. Now, how to write the time period for this? If it is in SHM, what do you do? I'll tell you one thing. Here you cannot write directly. You have to write, law of conservation of energy. Okay.
Sir, if K1, the spring K1 is stretched by X, then K2 will be stretched by 2X here.
Exactly, correct. We saw in pure rolling that velocity of center of mass, if it is VCM or VC, the velocity
sir.
at the topmost point will be 2VC.
2V.
The
Yes, sir.
acceleration of center will be, V. The acceleration at the topmost point will be
2V.
2V. And the bottommost point will be at rest in pure rolling,
0.
right? Okay, that will be 0.
Yes, sir.
So basically, if spring 1 extends by X, okay?
Yes, sir.
Spring 2 extends by
2X.
2x. The reason is simple. You can just check that. How?
Yes, sir.
When the spring goes a little forward, then the displacement of center of mass will be X. Okay.
Yes, sir.
Now, with respect to center, this thing will rotate by r theta, right? In this direction.
Yes, sir.
This thing will rotate in this direction by r theta, right?
Yes, sir.
Now, for pure rolling, r theta must be equal to X.
Yes, sir.
Right? Now, if center itself is moving towards right by X, with respect to center, if this is moving towards right by X, so with respect to ground, this point will be moving towards right by 2X, right?
Yes, sir.
And same thing for the bottom point. It is center is moving x towards right. With respect to center, it is moving x towards left. So this right and left will cancel each other, and the bottommost point will be at rest. Clear?
Yes, sir.
So basically, this is the whole thing is about all the rolling thing only. Here x and here 2x.
2x.
Now tell me, what is velocity of this related to? Velocity of this disk. Is it related to x or 2x? Is it the derivative of
I
x
didn't
or?
understand the question, sir.
See, अगर मैं बोला कि velocity क्या है center of this disk की, तो वो x का derivative है या 2x का derivative?
X का derivative है.
X का derivative, because center is moving by x ना.
Center, yes, sir.
If center is moving by x, the velocity will be dx by
Derivative
dt,
of
right?
x.
Clear?
Yes, sir.
Okay, fine, no problem. Now let us write law of conservation of energy. Total energy equals to half K1 x square plus half. Tell me.
K2 2x whole square.
Half
K2 2x whole
K2
square.
2x whole square.
Whole square.
Fine. Correct. What else?
Plus half.
Plus half
Kinetic energies भी दो रहते हैं इधर.
mv square plus
half I omega square.
I omega square. The reason is, see, axis of rotation is moving here.
Yes, sir.
When it is moving forward and backward, the center is moving and the axis of rotation is through center. So axis of rotation is moving. If axis of rotation is moving, then we have to write both, right? Translational kinetic energy and rotational kinetic energy, right?
Yes, sir.
So I'm mentioning it here. This is translational kinetic energy. Ke translational. This is
K rotational.
Ke rotational. And the things on the top are potential energies of the springs. Okay?
Yes, sir.
So this is PE1 and this is PE2. Okay?
Yes, sir.
So, okay, anyway, understand. Just by looking at it. Just for future reference, I'm writing. Okay?
Okay, sir.
So okay, PE1 and PE2 I'll write, you'll understand. PE1, PE2. Okay? Now problem is simple. You have to just solve, but there is one more thing. What is omega?
V by R आ जाता है इधर.
हाँ?
मगर ऊपर के केस में क्या बोलते हैं 2V by R आता.
नहीं, ऊपर का देखते ही नहीं ना, सेंटर का देखते हैं ना.
Yes, sir. Okay. तो V by R ही क्या था?
For omega, you have to look at the velocity of center, not the top. If you want to look at the top also, you'll get the same, because it will be 2V by 2R. 2V by 2R. Okay. Anyway,
okay. समझ गया sir, समझ गया.
We'll see the center. So omega will be equal to V by R. Okay.
Yes, sir.
Total energy बोलो जल्दी क्या है? Half K1 plus K2.
Yes, sir.
Into x square plus half mv square. Okay. Plus half I क्या है डिस्क का?
mr square by 2.
mr square by 2. Okay, tell me. V by R whole square. Clear?
Yes, I got it.
Okay, anyway. बोलो आंसर बोलो.
हाफ m को कॉमन में लेकर लेना.
Half K1 plus K2 x square.
Yes, sir. Plus half m into हम v स्क्वायर कॉमन में निकाल ले सकते हैं पूरा।
ओके, तो m की जगह क्या आता? 3/2 आता।
यस सर।
v स्क्वायर आ गया।
यस सर, समझ गया।
Now answer is simple. Instead of k, you write k1 plus k2. Instead of m, you write 3/2 m. Right? So time period equals 2 pi.
अंडर रूट सर m की जगह 3/2 m क्या लिया अपन?
देखो वहां पे ये r square कैंसिल हो गया, m/2 था और इधर m था, m plus m/2 3m/2.
ओके 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 ओके, समझ गया।
So your answer is
3/2, I mean 3m/2 into k1 plus k2.
clear? Okay?
Yes sir,
ठीक है।
clear.
So this is how you do if problems are given like this. Okay, fine. So I think we did lots of examples on how to find time periods,
Time
right?
period. Yes.
Okay. Now, I'll give you one this thing. Okay. Okay. This is one disk. This is another disk. Both are of different masses.
Okay sir.
Now there is a spring attached in between like this, which can twist. Okay, from the center of this to center of this. Clear?
Yes sir, clear.
So what we are doing is basically we are making the thing twist and leave. What do you mean we are making the thing twist and leave? So we will just give some small twist here and we'll leave. And this big thing is on the frictionless surface. Okay. So, you know, so I'll write this as I1. Okay. I1 is what? Moment of inertia about the axis of rotation, about which the spring is twisting also. This is I2. Okay. So this is I1. This is I2. Clear? Now I don't want to do this problem. It will be very big. But we did a similar kind of problem for two masses attached by spring and the spring was extending and compressing. Right? Clear?
Yes.
This problem. Which problem? This problem, right? And here your answer was 2 pi under root m by k, right? Sorry, 2 pi
Yes
under
sir.
root m star by k, where m star was reduced mass. Reduced mass was m1 m2 by m1 plus m2. Remember?
Yes sir.
Yes.
So I'll not do this problem. I don't want to do. Physics is that only. We'll do some problem. We'll derive everything. We'll understand
Okay.
everything. But if similar model comes, some little analogy comes. Okay, थोड़ा भी analogous रहा problem. तो हम लोग क्या करते हैं, instead of writing पूरा वो देख के जो है ना similar answer डाल देते. ठीक है. अच्छा.
Yes, sir.
इसका क्या था आंसर जो 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 आज इंट्रोड्यूस करे हम लोग ट्विस्टिंग का 2 pi under root I by k था ना, राइट?
Yes.
तो वो दो those two problems I will take the knowledge of those two problems and write the time period directly here. See, time period is equal to 2 pi under root
I1 plus I2 by क्या था?
I2 by I1 plus I2
Okay.
into k. Clear?
Yes.
Okay. So if you want, you can do, if you have time for practice. You should write, rotational kinetic energies of both. Okay. And what will be the energy stored in twisted spring? Tell me. Energy stored in a compressed spring is half kx square, na?
Yes, sir.
So
Yes.
energy stored in a twisted spring will be half k theta square.
सर इधर
Theta
1 by
square,
I1 plus
yes.
1 by I2 करें ना अपन,
कौन सा?
मतलब यहाँ पे जो अपन मोमेंट ऑफ इनर्शिया लिखे उसमें 1
Reduced
by
moment
I1
of
plus
inertia.
1 by I2. Okay. अच्छा
Reduced moment
समझ
of
गया.
reduced moment of inertia.
लीनियर पैरामीटर्स को एंगुलर पैरामीटर्स में लिखे बस.
हाँ बस. Actually पास्ट में बहुत सारे चीजें करे. Like न्यूटन सेकेंड लॉ को भी वैसे ही करे. F is equal to
Yes,
ma
sir.
था.
हाँ.
ठीक है. Tau is equal to I alpha लिख दी. ठीक है. और एंगुलर मोमेंटम भी वैसे लिखे थे. L is equal to I omega. Actually linear momentum was mv. तो एनालॉजी लेके लिख लिए क्या I omega. बराबर?
Yes, sir.
Yes, sir.
Okay, fine. What is the time?
5:35.
Okay, we'll continue tomorrow. I'll share this. You just go through. So tomorrow we'll see some problem involving friction also. Friction and normal reaction. Okay.
Okay.
Yes, sir. Okay.
So in SHM, how we'll combine the concepts of friction and give. Actually, I did one already. What will be the maximum amplitude for slipping not to take place and all. We'll do some more problems and all varieties of problems we will see. And we'll combine circular motion also tomorrow. Okay?
Okay, sir.
Okay, fine.